reason that's important is that the effective resistance of each element is called the reactance. And those elements actually that I'm talking about are the capacitor and the inductor. So resistance is just resistance, and the symbol for it is this. The capacitive reactance is a formula that's put together when you have the capacitor in order to get an essential resistance that you can work with in a circuit, and it's called reactance. And as I'm sure you already know, the symbol for capacitors here. Symbol for an inductor is this one, and the inductive reactance is XL, and that again is a sort of a kind of a resistance, an effective resistance that we use in an AC circuit in order to solve for the information about the inductor. Now, in an AC circuit, each of these three elements, capacitor, inductor, resistor, all react differently to current, right? So here, if we have just a graph of current, and at this point, so at point time 0, okay, we have the current flowing here. In the resistor, what happens is the voltage in the resistor follows the current, all right? So when the current here is at its max, the voltage here is at its max. So what we say is that the voltage across the resistor is in phase with the current. For an inductor, the voltage across the inductor lags the current by 90 degrees. So you can see here that it's just behind, all right? It's behind, and we know that this point here is 90 degrees because this whole piece is 360, all right? So we're lagging, the voltage across the inductor lags by 90 degrees. And most of this really is just information. You don't have to worry about it too much. And the voltage across the capacitor leads by 90 degrees. So voltage across resistor is in phase, voltage across the inductor lags by 90 degrees, voltage across the capacitor leads by 90 degrees. Now, if we have a series AC circuit, which is what we have right here, and again, all I'm concerned about right now is thinking about the complex numbers and what that looks like. So we see we have a resistance, we have a capacitive reactance, and an inductive reactance. And what we do is we put them on the X and Y axis. So the resistor is what we call real, and it goes on the real axis. So whatever amount that resistance would be, let's say it's 12 ohms, right? That 12 ohms would be here. Our XC goes on the y-axis, and it goes in the negative direction. So whatever amount we have there, that's shown up here, or drawn here. Our inductance is on the, or I should say inductive reactance is on the y-axis as well, and it's in the positive direction. So if we had a number there, we'd write it down here. Now, here we have a circuit. Can't really solve for the circuit because we do not have a current, but I'm just going to talk about what we would do here to solve for the mass of these sort of resistant pieces. So we'd think about, okay, so I'm on the X and Y axis. I have 45 ohms resistance, so that goes on the real axis in the positive direction. So there's my resistor, which is the 45 ohms. My capacitor, or my capacitive reactance, is 60 ohms, and that goes on the y-axis in the negative direction. So I go down here, and that's my XC, and it is 60 ohms. My inductive reactance is 72 ohms, and it goes on the positive y-axis. So that 72 ohms, or the inductive reactance, goes up here. So our XL is here, and it's 72 ohms. So now what we do is we add up the y-axis, because especially for a circuit like this, a series circuit, you want to find the total effective resistance. So we have 72 going up, 60 going down. So we can just redraw this. And we end up with essentially 12 going up when we add the two together. So the 72 minus the 60 gives us 12 going up on this y-axis, all right? So that's the XL minus XC. And we still have our resistance, oh, and it's 12 ohms. Okay? And we still have our resistance, which is the 45 ohms. Okay? It's supposed to be resistance. So now we have 45 ohms here. We have 12 ohms here. So what we can do is solve for what's called the impedance. Alright? And I need another piece of paper here. So essentially what we have is our 45 ohms, which is the resistance, okay, and our 12 ohms, which is the sum of XL, so XL minus XC. And what we want to solve for is the impedance, which is essentially the total resistance of this circuit. And you can see that it's, in order to add these two together, we have to use Pythagoras. So this here, what we're solving for, is called Z, and that's impedance. Alright? So in order to get that, we use Pythagoras. So then, our impedance equals the square root of 12 squared plus 45 squared. And we end up with 46.57 ohms. Okay, that's our impedance. The other thing we need to know about the impedance is we need to know that angle. And it's typically the angle against the horizontal axis. So we need to know what this is. So what we're doing is coming up with an answer that's in polar form. Alright? In order to find theta, we do the inverse tan. So tan to the minus 1 of opposite, which is 12, over adjacent, which is 45. Okay, so we end up with second function, what are we doing here, tan 12 divided by 45, close bracket, equals 14.93. I'm just going to round it up to 15, alright? So 15 degrees. So our impedance then for this circuit is 46.57 ohms, angle 15 degrees. And depending on your instructor, you might need to have more digits in there. I was just being a little bit lazy. Alright, and that's basically solving for your impedance. If you had more information here, you could solve for other things, but I just wanted to give you an idea of what you'd be looking at in the beginning. Alright, so this video has